This lesson is how to graph secant and cosecant functions. The graphs of secant and cosecant are also periodic in nature, but look very different from the graphs of sine and cosine. In particular, these graphs have a series of vertical asymptotes where the functions are undefined. For instance, let's look at the graph of y equals cosecant x. This doesn't look much at all like the graph of sine, but there are similarities. For instance, if you'll notice, cosecant has a series of asymptotes, of vertical asymptotes that is. And these asymptotes are occurring at multiples of pi. Sine, on the other hand, has no asymptotes. But at multiples of pi, the graph of sine is at 0. So one should expect that, cosecant, which is 1 over sine, would be undefined whenever sine is 0. And that's exactly what's happening. And we'll explore other relationships between cosecant and sine as we go further through these lessons. Y equals secant of x looks very similar to cosecant. In fact, the only difference is phase shift. If you think about how sine and cosine are related, they look almost identical, except for a phase shift as well. Some important aspects of secant and cosecant, as with any function, starting with the domain. The domain is all the points that you could put into the function and get a real number back out. So this is occurring at every single point where there's not a vertical asymptote. Generally, we would write the domain in interval notation, but because of this infinite number of asymptotes, it's not a very good way of expressing the domain of cosecant. So to express the domain of cosecant, we tend to write it in terms of what's called builder notation. So builder notation generally looks like the set of all values x, and then this colon means such that. So all values x such that x does not equal n times pi. And n is an integer value here. So I'm not going to write n as an integer, I'm just going to leave it as an understood thing. And that means if n is an integer, it could be negative numbers, it could be 0, or it could be positive values. So if it's positive numbers, 1 times pi is pi, 2 times pi is 2 pi, and so forth. Those are all undefined values. 0 times pi is 0, it's undefined there. Negative pi, negative 2 pi. So this would tell us exactly where all those asymptotes are, and because its x does not equal those values, it's telling us that we can't include those in the domain. Now the range of cosecant. So the range is all the possible values that are defined along the y-axis of a function. So if you can imagine squashing this graph up against the y-axis, starting with this local minimum right here at positive 1, and going from there up to positive infinity, you would have some value along all those points. But there's kind of this gap between positive 1 and negative 1. So we come down here, and this is a local maximum, which occurs at negative 1. And starting with negative 1 and then going down to negative infinity, if you're imagining this graph being squashed up against the x-axis, you would see points defined all along that interval as well. So all the way down to negative infinity. But there would be a gap between negative 1 and positive 1. So the range here is from negative infinity up to negative 1, but it includes negative 1, and then it goes from positive 1 up to positive infinity. The period of the graph is how long it takes for your cycle to repeat. So let's say we start our cycle at 0. Then follow along until you start seeing a repeating graph. So far nothing's repeated. This next portion of the graph is similar, but it's still not repeating because everything's negative along this interval. It isn't until we reach right here that we start seeing the repetition. So that means by this point right here, that's how long it takes for this entire cycle to complete. So the period is 2 pi. Now, a similar way, you can come up with the aspects that are pertinent to secant of x. So the domain, it's a little bit different because the domain here, multiples of pi are defined. It's these points right here, like this is pi over 2. This is 3 pi over 2. This is negative pi over 2, negative 3 pi over 2. These are the values where the asymptotes are occurring, and we need to exclude those. So when I express my builder notation, it's all the values x, such that x does not equal, well, how do we express this? It turns out one thing you might want to try is saying n times pi over 2. Problem with that is if you have n times pi over 2, if you plug in 0, that would be 0. So you're saying that 0 is undefined. But there's no asymptote at 0, so that doesn't count. Similarly, if you put in 2, it would be 2 times pi over 2, which is pi. But pi is defined. So this doesn't exactly work. But if you'll notice, all of the multiples of pi here in the numerator are odd numbers. So if we express this as 2n plus 1 times pi over 2, what this accomplishes is n is an integer, then any integer value that I put in, it's multiplied by 2, which makes that a even value. So 2 times n is always going to be an even number. And 1 more than an even number is an odd number. So this 2n plus 1 guarantees that I'm working with an odd multiple of pi over 2. Similarly, if I plug in an integer, there's no way that I could get 0 out here. So I put n equals 0, 2 times 0 plus 1 is 1. So I'm safe there as well. So that's the domain of the secant. The range is the same. So the range is still from negative infinity up to negative 1, and then union 1 to positive infinity. The 1 and negative 1 are included, and the period is also 2 pi.
One last thing I would like to mention about these graphs is that there is no defined amplitude for the cosecant or secant graphs. And that's because these graphs go off to infinity at multiple points along their domain. However, when we are graphing secant and cosecant, we will take advantage of the use of knowing how to graph sine and cosine in order to produce the graphs of secant and cosecant. So when you see me do examples, I will state that I'm using an amplitude, but that's because I'm using the amplitude of a sine or cosine graph rather than the amplitude of a secant or cosecant, which isn't technically defined.
Now, I'd like to explore with you where the shapes of these graphs really come from, and for that I have a couple of applets that I want to show to do that for you, and then after that I have a couple of applets that I want to show how transformations are affecting these graphs. So let's get those started. Let's begin with cosecant. So I have the same basic setup as how we explored the shape of sine and cosine. So I have a unit circle to the left that has the center essentially at 0, 0, and point P is any point along that unit circle. So the maximum distance is always from the center is going to be a radius of 1. Cosecant is defined as 1 over the y value of that point P. And if you'll notice right now, the y value of this point P is 0 because the coordinates of this point is effectively 1, 0. Because if I kind of imagine an axis here on this circle, this would be the coordinates 1, 0. Now, given that, you'll notice that the value of cosecant right now is 1 over 0, which is essentially infinity. So I have an asymptote at 0. But if I start moving point P around, now I get some points that are defined. They are decreasing in value currently, and they will decrease until I get to pi over 2. And at pi over 2, the value of cosecant is equal to exactly 1. That's the local minimum that I'm going to reach at this particular branch. If I continue rotating around, I am going to continue to see this U shape that I was seeing earlier, to a point where when I get back to positive infinity again. And the graph tries its best to plot that at infinity, but it's, should be an asymptote there. If I continue rotating around, now my y values are negative. So when I divide 1 over a negative number, I've got this U shape again, but it's flipped vertically, basically. The local maximum that this is going to reach is at 3 pi over 2, which is going to be negative 1. And then as I continue rotating, it's going to start to decrease down to infinity again. So essentially, my graph is going to contain 0 as an asymptote, pi as an asymptote, 2 pi as an asymptote, and so forth. But the way I'm drawing these graphs, you can't actually draw an asymptote. You can't make it part of a graph. It's only the dashed line is only a visual feature to help you recognize that is undefined at that particular point. Now, if we take a look at the cosecant graph, you'll see that the shape is correct as we expect it. The location of asymptotes is also correct. Notice that they are always multiples of pi. Okay? All right, let me get rid of the asymptotes that I've drawn in. And the next thing I want to show you is this. So, when it comes to drawing the graph of cosecant, it helps to, in fact, draw the graph of sine. And then, from there, decide what you want your graph of cosecant to look like. So for instance, let me show you what the graph of sine looks like with respect to my cosecant graph. Notice that whenever I have an asymptote, the sine is equal to 0. So if I draw my sine wave, and I have a point that results in an x-intercept, or a 0, that's where an asymptote is going to be. So I'll draw my asymptotes there. And wherever sine has a local maximum, that's where cosecant has a local minimum. They kind of just touch each other. And similarly, where sine has a local minimum, the cosecant graph has a local maximum. So basically, if I can draw the sine wave in, then I can come up with a pretty decent graph of cosecant simply by plotting asymptotes at the values of 0, using these local minimums and local maximums to tell me where the center of that U shape is going to be, and then just draw in, approximately what that U shape is supposed to look like. And that's a pretty effective way of coming up with the graph of cosecant. In fact, it's probably the recommended way of all instructors that you'll run into, is to just draw the graph of sine first, and then come up with the graph of cosecant afterward. Now that we know where cosecant comes from, secant really is no different. If I'm just using the x value of this point P around the unit circle, and doing 1 over the x value, and what you'll find is that results in the same U shapes, but it's just off by a phase shift of the cosecant graph, which is okay. Now, that gives you an idea of where the shape comes from. The same relationship between sine and cosine exists as secant and cosecant. So what I mean is, if I show the graph of secant now, and then I show the graph of cosine, you'll notice that wherever cosine has zeros, you have asymptotes in your secant function. Which should make sense, because if cosine is 0, then secant is the inverse of that, so 1 over 0 is undefined. That's where these asymptotes occur. And then wherever cosine has maximums and minimums, that's where the lowest and highest points are on these U-shaped portions of the graph. So you can effectively just draw the graph of cosine and then fill in what secant is supposed to look like. Let's take a look at the transformations of the graph of cosecant that can occur. Notice the same sort of transformations exist with cosecant as did with the sine graph. So for instance, we have this value c, which is a vertical shift, this value a, which was an amplitude change, this value b, and this value d. D was a phase shift, and b is a period change. So the changes that can occur here can be affected by these constants. Now, let's look at amplitude first, because we said that amplitude really isn't a factor when it comes to cosecant or secant, but it sort of is. It's just a little bit different than what happens with sine and cosine. So if I change the amplitude to 2, for instance, notice that the minimum values that, or the local minimums that the cosecant reaches and the local maximum that the cosecant reaches is positive 2 and negative 2. So whatever this amplitude is, that is a location of the local minimums and local maximums that the cosecant is going to reach. So it's similar to the amplitude of sine and cosine, but not exactly the same. Also, if you change down to lower values, it would come closer to the x-axis. If you'll notice, the graph tends to become distorted when you get that close. It's just because when your graph is going to positive and negative infinity, strange things can happen with numerical accuracy. If you go to a negative amplitude, then your graph flips about the y-axis. Okay, let's put the amplitude back to 1. Now the period change, the period is, this same sort of concept as with sine and cosine. So if I change my period to 2, then what that means is, the graph's going to complete a full cycle in half the amount of time, or you can look at it as it will complete 2 full cycles by the time you get to 2 pi. However you want to look at that, it's fine. Bring that back to 1. A vertical shift does exactly, phase shift. The vertical shift does exactly as you would expect it to. It just moves the graph up and down, and the phase shift just moves your graph left and right. Now, let me let me get back to where I began here. Now, with everything reset, the next thing that I want to show you is what happens with the graph of sine. Because as I said, the easiest way to graph cosecant is to graph sine and then just fill in the u-shapes. So the same changes are going to occur to this sine wave as to the cosecant graph. So let's watch what happens. If I change the amplitude, the minimum and maximum values where that sine has is still the same exact points where the lowest points that the cosecant reaches, or the highest local points that the cosecant reaches. If I apply a change in period, there is a similar change with cosecant. If I apply a phase shift or even a vertical shift, the same relationship occurs. So no matter what translations you have, you can always just draw the graph of sine first and then fill in the gaps as to what the cosecant would look like. With your final answers, however, wherever you do have vertical asymptotes, you should always draw those in. Let me get everything back to where it starts here. Okay, so wherever you have zeros for sine, you should include in your graph the vertical asymptotes. The reason I'm not including them here in this applet is because you have to calculate where each one is, and it's very complicated to calculate that with the changing number of asymptotes that could occur on screen at once. So just know that you will need to include those in your own graphs. The transformations of secant are no different. Essentially, you want to draw the graph of cosine first with any changes that may be affecting your graph. And once you draw your graph of cosine with any changes that may occur, then fill in what cosecant should look like. That's the simplest way of doing these. With that in mind, let's work a few examples of graphing secant and cosecant graphs. So have y equals 2 secant 1/2 x, and secant is related to the cosine function. So essentially I'm going to draw the graph of cosine, and then I'm going to fill in the gaps from there. So the changes that could occur: amplitude, period, phase shift, or a vertical shift. And let's just describe which of these are occurring first and then go from there. So there is no vertical shift, so my cosine is going to have a horizontal axis at 0. And I'm not calling that an asymptote. It's not an asymptote. It's just a horizontal axis to bound between, that's all. The phase shift, there is none as well. Amplitude, it has an amplitude of 2, which means cosine is going to go between +2 and -2 on my graph. And then the period change. So the period for cosine is usually 2 pi, but now I take that number b, divide 2 pi by that number b. So 2 pi divided by 1/2 is 4 pi. So 4 pi is the amount of time it's going to take me to complete one cycle. Okay, now to fill this in, I know the graph of cosine. It starts at its maximum value when you're at 0. So at 0, cosine is going to be up here at 2, which is the maximum distance away from my horizontal axis. It's going to take 4 pi to return back, and 4 pi isn't exactly on my chart here, but it's going to be somewhere, say like right there. Which means that, this is a periodic thing. You can deduce that halfway in between there, you're going to have your minimum value. So halfway in between at -2, at 2 pi, you'll be at -2. And then halfway in between those two intervals, you'll be at 0, so at pi and 3 pi. And as you get comfortable with drawing these graphs, you can do things like that. Or if you want to, just kind of think of the cosine wave, you have to kind of know that cosine starts at its maximum and then goes back here and reaches its maximum by 2 pi. So this is what happens at 0, at 2 pi, this is at pi, and this is pi over 2 and 3 pi over 2. Now the thing is, this maximum that you're reaching, and then this 0, then the minimum, and then the 0 again, and then the maximum back at 2 pi. This has to happen in twice the amount of time, because your period is divided by 1/2. So if you take 0 divided by 1/2, whoops, not pi over 2, sorry. 0 divided by 1/2, that's still 0. If you take pi over 2 divided by 1/2, that's going to be pi. If you take pi divided by 1/2, that's going to be 2 pi. 3 pi over 2 would be 3 pi. So basically, now your maximum occurs at 0. This next 0 point occurs at pi. Your minimum, 2 pi, and so forth. So that's kind of the logic that I'm using here. And I'm going to go ahead and fill in, going the other direction as well. And cosine, I'm just going to draw in as basically a dashed line, because it's not really part of my cosecant graph. I'm just using it as reference. Okay, and honestly, you don't even need to do that, because you know where the zeros are, you know where the maximum and minimums are. That's really all you need for cosecant. So I'm going to do my graph of cosecant in green. Wherever I have zeros, I have asymptotes. So I'm just going to draw those in. Wherever I have maximum and minimums, that's the local maximum and minimums for this U shape of my cosecant graph. And you don't need to fill in everything precisely in between. You just need to basically make that U shape, that the function contains. And that's a perfectly valid graph. That works just fine. Y equals 3 cosecant of the quantity x minus pi over 4. Okay, so again, identify the different changes that are occurring. So we have amplitude, period, phase shift, and a vertical shift. Okay, in this case, there is an amplitude change. The amplitude is 3. Period, there's no multiplier on my x, so there's no period change, so it's still just 2 pi. The phase shift, there is a phase shift. It's going pi over 4 units, but be careful on the direction. Since it's x minus pi over 4, it goes in the opposite direction of the sign, so this is going to the right. And then the vertical shift, there is no vertical shift. So cosecant is related to sine. So my sine wave, as I'm drawing that, I just need to be thinking of what my sine wave looks like in general. It starts at 0, then goes up to its maximum, back down to 0, down to its minimum, back up to 0 by the time you get to 2 pi. Alright, so I'm just going to be thinking of that as I am drawing this graph. So I'm going to draw sine first. Now, the amplitude is 3, so it's 3 units away from the vertical axis. So I'll just indicate that. Only other change here that I need to worry about is the phase shift. Alright, so the phase shift of pi over 4. So if I look at my units that are marked here, here's negative pi. Halfway in between that would be negative pi over 2. So here's negative pi over 4. Alright, then that means halfway in between here is pi over 4. This is pi over 2, 3 pi over 4, and so forth. Okay? Now, the graph is shifted to the right by pi over 4. So that means my starting point of this wave is going to be right here at pi over 4. The end point is also going to be shifted pi over 4 to the right of 2 pi, where it should be ending. And every other point in between is going to be the same. Is going to be shifted in the same way. So for instance, when I go up to reach this maximum that's going to occur, that's going to be pi over 4 units to the right of pi over 2, where it usually occurs. So that's at 3 pi over 4. Then I'm back to 0 right here. Then I'm down to negative 3 right here. So this gives me enough to get an idea of what's happening with my sine wave. And so basically, if I wanted to fill in the rest of these, which I absolutely could, that would be fine. Most of the time you only need to draw one cycle. So that would be fine in this case. So I'm going to draw asymptotes wherever those zeros occur. And I'm going to use these maximum points to indicate the local minimums and maximums of this U shape. And I'm not going to draw it any further than that. I'm just going to draw one cycle, and that's appropriate. As long as that cycle is labeled properly, there's nothing wrong with that whatsoever. Graph y equals 2 plus 3 secant of 2x minus pi. Again, we just start identifying the different changes that could occur. And there's no particular order you need to do these in, just how you recognize them. So the 2 that's added to the function is a vertical shift, so we're going to go up 2 units. So I'm just going to indicate that with this dashed line right here, so I kind of know that that's my horizontal axis that sine is centered about. The phase shift is a little trickier because that 2 is inside these parentheses. So I need to factor that 2 out. So I need to write this as 2 plus 3 secant 2 times the quantity x minus pi over 2. Now I can visibly see that my phase shift is pi over 2 units to the right. The phase shift, oh, sorry, I don't know why I called that phase. The period change. period change here normally is 2 pi, but since we have that multiplier of 2 on the function, on the inside of the function, the period is now pi. So it's only going to take pi units to complete one full cycle. The amplitude is 3, so we're going to reach a maximum of 3 units above the horizontal axis, which means that would put me at positive 5, and then 3 units below, so at negative 1. Okay? Yeah, let's draw the graph of cosine, since secant is related to the cosine. And I'm just thinking in my head what the original graph of cosine looks like. It starts at its maximum, goes down to its minimum, then back up by 2 pi. So this is at pi, 0, pi over 2, and 3 pi over 2. So that's what I'm thinking of as I'm drawing this. Now, the cosine is going to be shifted pi over 2 units to the right. So let's start there. So pi over 2 is going to be here, halfway between 0 and pi. This is going to be negative pi over 2. So that means I'm going to be at a maximum at pi over 2. Now, the period change. So everything's going to wrap up by pi units. So instead of wrapping up at pi over 2 units past 2 pi, it's not going to be that far away. So I have to account for this. Good way to do this is, something like the chart that I showed you before. Cosine reaches its max, 0, its minimum, 0, and then its maximum again. Alright, for the original graph of cosine x, the maximum occurs at 0, pi over 2, the minimum at pi, the 0 at 3 pi over 2, and then the maximum again by 2 pi. So let me get rid of that graph, because that's really what this chart is representing. Okay, now, if I have a phase shift, all of that gets moved pi over 2 units to the right. But let me do this. Let me apply the period change first. So the period change, if I say cosine 2x. Now, that means everything has to wrap up by pi instead of 2 pi. Okay, so that means this minimum is pi over 2, this is at pi over 4, and this is at 3 pi over 4. Essentially, if you just go through and divide each of those by 2, that's what you come up with. Now, the phase shift. So cosine 2 times x minus pi over 2. So I'm shifting everything to the right by pi over 2. So I'm just adding pi over 2 to each of these points. So pi over 2, 3 pi over 4, pi, 5 pi over 4, and 3 pi over 2. And you can verify those with just a little bit of work with fractions. So for instance, pi over 4 plus pi over 2 would be the same thing as pi over 4 plus 2 pi over 4, which would be 3 pi over 4. So that's where I'm coming up with those numbers. But that tells me, these important parts of my cycle. So 3 pi over 4 would be right here. This would be pi over 4, 5 pi over 4, and then eventually somewhere out here is going to be 3 pi over 2. So at 3 pi over 4, the function cosine is back to its 0 point. At pi, we are down to our minimum, which is at -1. and then by 5 pi over 4, which is right here. Maybe I should label these in so you can see them better. By 5 pi over 4, we're back to our horizontal axis. And by 3 pi over 2, we're back to our maximum. So that would be one full cycle of the cosine. Now, for one full cycle of our cosine, what we need to consider now is where do the asymptotes go? Where do these U-shaped pieces go? The asymptotes are going to go wherever cosine hits that horizontal axis. So in this case, I'm going to have an asymptote here at 3 pi over 4 and at 5 pi over 4. These are the maximum and local minimums and local maximums of the U-shaped portions of this secant graph. That is one full cycle, and that's perfectly fine to just draw that much. You're certainly welcome to add in the rest of the cycles if you like, but since it's periodic in nature, if you can get one cycle in, that is just fine.